so you should now see the slide project management, right? You're seeing that okay? Great. Okay, good. So we'll go on here. All right. So this is the first start of what we're talking about in terms of project management. So the initial question that everybody has is, what is project management, or what is a project? So the formal definition of a project is a complex, non-routine, one-time effort limited by time, budget, resources, and performance specifications designed to meet a specific need or needs. That's a project. If you're building a house, that's a project. Okay, you can see that there are certain limitations of resources or time that has to happen if you're building a house. But there's other kinds of projects too, like setting up a new restaurant, designing a French dining experience. I've got an example here. Holding a workshop. Those are all separate projects. They are all a non-routine, one-time effort. Most projects have very common characteristics. They have a clearly stated objective. There's a reason for it happening. There is a lifespan. There's a beginning to the project, and there is an end to the project. There can be multiple people or multiple entities or multiple institutions working together on the project. Many times, a project is something that has never been done before. So obviously, there's been a lot of people who have built megasats and a lot of people who have built LACES payloads, but you have never done that before. So that is new for you. So that fits that definition. There are restrictions. Most projects are restricted somehow: time, cost, performance. You are obviously time limited. You've got a specific beginning and time. There are going to be resources which are provided, so you are limited in terms of your cost, and then performance. So those are the kinds of things that happen with a project. There are particular reasons why you want to make certain that you look at managing your project, and that is, you want to make certain that you get your goals done and your objectives within those constraints. There are trade-offs that you're going to approach between time, cost, and performance, right? So, what we'll talk about a little bit later on is that there's this engineering triangle. So on each of the apex of the triangle is cost, performance, and time. And it's basically the caption underneath that is pick two. So there's always an optimization that has to be done during a review. You don't have infinite time, you don't have infinite money, and you can't do things to unlimited accuracy. So there's always going to be a trade-off. Everything breaks at some point. There is always going to be a problem. Murphy's laws exist for a reason, and that is because there's always problems in life. I mean, these last 2 years have taught us undoubtedly how many problems that there are in life, but there's a lot of people that go through and we manage to overcome this stuff. So that's another reason why you want to manage a project, because of unlimited events that or unexpected events that happen. Oh, here's that phrase that I mentioned earlier. Risk planning is an essential component to project management, or risk management is the essence of project management. Okay. There are unique features, special features that happen in a project. And so you want to be able to take into account. As your project complexity increases, that becomes even more difficult to try to complete. There's a lot more moving parts, if you will, that have to be coordinated. And the risk for any one of these parts blowing up in your face has increased. If you're starting new technology, that is usually increased risk and complexity. So there's a number of things. So there's a lot of reasons why you want to be putting together project management. So the team structure, right? And many times what we do is in the project is that you develop a dedicated project team structure in this. And that's a independent team with specialists, software, mechanical, electronics, documentation, I don't know. There could be a lot of specialists that work together and are focused exclusively on completing a project. That's the team. There's real good advantages of a team. You can get a cohesion, there's a focus, you can respond to problems quickly. There can be issues like resistance to outsiders outside the team or constrained staff expertise. You got a software person and a mechanical person, but you don't have an electronics person. How are you going to deal with that? Very appropriate. Teams are appropriate for complex or organizations with many different projects. And one of the exercises that we talked about here is the team contract. I mentioned this a little bit earlier. There is a activity which is on the ACES website, and you should start thinking about working on this activity tonight, right, as you're going to be going for it. Forming, storming, norming, performing, adjourning. Okay, those are the 5 stages of team development. Forming, this is where you're getting acquainted and starting to discuss the ground rules, how your roles are going to be distributed, and what the interpersonal relationships are. After that, there's usually some discussion about how those roles and project constraints are going to be applied or contested. After one gets through that sort of conflict resolution, now you're into the point where you're starting to develop team cohesion and starting to work well so that you can really establish the performance that goes on when you're really kicking into working as a team. Towards the end of the team, there can actually be some psychological problems with breaking up the team, because depending upon how the team works, you can develop really close relationships. And now all of a sudden you aren't working on the project anymore. So you got to just be aware that once you finish the project and you start moving on to other things, you'll still have the friends that you made, but it isn't going to be quite the same thing anymore. So those kinds of stages exist, and they're universal across these different teams. So the team contract is part of building your project team. You need to be thinking about the ground rules. How are you going to plan the project? What are going to be the roles? Who's going to be doing what, when? What about progress? How are you going to track progress? How are you going to assess it? What happens if somebody who is responsible for a particular task fails, doesn't do their job? What do you do? Okay. How do you accomplish that? You're still on a timeline. You still have to complete all these tasks. How are you going to handle that? When there are changes to your payload, to your design, how are you going to document that? How are you going to make certain that everybody understands what those changes are? When are your meetings? How are they going to be scheduled? How are you going to be run? In my experience, I actually prefer more shorter meetings rather than fewer longer ones. Each meeting should have a focused agenda. It should be time constrained. You should not be going on for, okay, we're going to discuss the payload today and going on for 2.5 hours. That's a really good way to kill yourself and your project, right? Today, we're going to focus on the electrical power system for subsystem B, right? Make certain that you bring your ideas and proofs to the meeting. We'll be running for a half an hour, all right? So meetings which are crisp, which are focused, which are more frequent, shorter rather than longer. You need to have a team identity. What's going to be your team name? You should have a project with an appropriate project name, something that sort of identifies yourself as a team and your project as with your shared vision. Make certain that when you're doing your team contract that you figure out how to facilitate discussions so that you can still identify underlying problems without generating conflict. All right, that's a really important part. Figure out how you're going to foster consensus and follow up on solutions, right, to get implementations. So that's sort of working together in that bullet that I'm talking about there. That's a real important part that you want to think about how you're going to do that. And there's going to be conflicts. You're going to have arguments. But the key is, how are you going to manage that? How are you going to make those discussions and those conflicts so that it isn't, people don't go away with hurt feelings, that they actually understand that they're heard and that their issues are being taken into account. Right? You need to be thinking about these things. You need to be writing down how you're going to be doing this kind of stuff, right? Teams can have problems. You gotta watch it, right? You need to be aware of these kinds of pitfalls that happen. A team, and I've seen them. A team can be convinced that its decisions are infallible. We've made this decision and therefore it's great. There's a real classic example of a Mars probe that NASA sent to Mars back in the early 1999, something like that. It had an orbiter and a lander. Both of these systems failed. All right, both the lander and the orbiter failed. And what was discovered later on was that the teams which were responsible for the flight and the tracking systems didn't talk to each other. They each thought that they had the solution. One group was working in imperial units, feet per second, miles, blah, blah, blah. The other one was working in metric. And they didn't do the right conversions between the two. So the orbiter basically crashed into Mars instead of going into orbit. So teams can think that they know exactly what they're doing, but if they don't communicate, and if they don't listen to the other teams, there can be lots of problems. You need to examine solutions and other alternate plans. Don't stereotype outsiders. People who come in with criticism, you need to listen to what they're having. Right? So there's a variety of things that you need to just be aware of. Every project has a cycle, right? And there are particular phases that every project goes through. So here's sort of that cycle. So you start with the design. That design leads to what's called the preliminary design review. After that is completed, you're into development, right? Which then results in the critical design review. And after those two phases, then you start building flight hardware and software. You're not building any flight hardware or software before the CDR is completed. Once fabrication is done, you then have to put all the bits and pieces together. They have to physically fit. They have to be the right pieces together. And then once you are done with that integration, then you're going to test it. You're going to test it to make certain that it functions properly during flight. And at the end of that, you then have your flight readiness review, and completing that, you go into operation. So this is the cycle, right, that happens. So design. So what happens during design? Nothing hardware happens during design. This is a paper study. What you're doing here is that you're identifying, particularly in the pre-PDR, the only thing that you're doing in like the pre-PDR is that you're defining your goal, your objectives, and your requirements. That's basically all you're doing. You're spending this time up front in planning your project. What is it that you're trying to do with this project? That's what you're going to be doing with the initial phase of your program during your design. There's some system level design that you'll do, which would be satisfying your requirements once you get those identified. And then once you're done with all this, you write this up into your preliminary design review. But there's no soldering, there's no software programming, there's nothing. It is basically what kind of science are we going to do, and what are the requirements? What does that science say that we have to do in the thing? And we'll talk a lot more next Tuesday. We'll talk a lot more about the system design phase and how you determine requirements, et cetera, goals, et cetera. Development. So after you're done with your PDR, you then go into development. Development is a detail, and this is sort of the flow chart that you see here. So design, prototype, test, do over. Okay. So what you're doing during development here is that you're prototyping. You're prototyping some of your electronics. You're producing sensor interface circuits. You're prototyping subroutines. You're testing different ways of constructing your payload mechanical system. You're not building flight hardware, right? All that you're doing is that you're gaining information that then leads to your next phase, right? In here. So the other thing that you do during development phase here is that if you have particular long lead items, things that might take weeks to come in, you probably need to commit to those and get those purchased then. You start identifying what your pre-flight phases are going to be. What are you going to be doing during fabrication, integration? What calibrations do you need? What testing are you going to do with your subsystems as well as your integrated thing? All throughout these phases, you're going to be doing a risk assessment. What are the potential things which will come up and bite you? Once you're done with development phase, you go to your critical design review. Many times I talk about, not many times, all the time, I talk about the CDR document as your build to order document. This should be your assembly guide. I should be able to take your CDR document and give it to a completely different group and have them build according to that CDR and deliver that back to you. And you should be happy with it, right? So you need to have all your detailed specifications and drawings, et cetera, and final designs and parts lists, et cetera, in that CDR. After your CDR is approved, then you start fabrication. Notice the way that fabrication actually works here. What we do is that there's two parts here. So you need to order parts, and you need to do quality assurance, quality checking with those parts. You got to make certain that the parts that you have are functional. So, for example, let's suppose that you need a resistor of a precise value, and you determine what that value is. Well, there's two ways you can go. One way, you can go and you can pay the extra money and the extra lead time for precision resistors. The other way is that you can buy 100 resistors of that type and go through and test each one and only accept those which are within your spec. It's the same thing. Okay? So you can do QA, QC on your parts. You ought to make certain that everything is correct according to what you did. There's probably some training that might be, and then you're assembling your subsystems. Each subsystem is inspected and separately tested. If it looks okay, then you can go on to a thermal test. If it survives the thermal test, then you do integration. At any stage around here, you may have to go back if there is a problem. If the solder joints aren't really up to spec, go back to assembly and resolder them. Right? If you run into a cold solder joint, which is generally many times revealed during thermal testing, you fix that, go back. Okay. All right. Once you complete this, then you go on to integration. Integration is when you're putting together the final package. Notice that we start off with a fit check. Right? Does it actually go together? Do the screws go in the holes? Do the boards integrate with the structure? And if it does, fine. Then you can integrate it and you can go through testing. If it doesn't, then fix the problem and come back to that. Also notice that during integration, you're putting in your software. And the same thing applies here. Does your software fit? Does it work? Right? Or is it throwing errors? And if it does, great. If it doesn't, then you do it all again. By the time you're done with this integration, you should have a flight-ready payload, or what should be a flight-ready payload. In which case, you go through and you do system testing. So system testing is a formal way of documenting your payload functionality, right? Once you have your flight-ready payload, you do your functional test. Those functional tests should have been defined in your CDR. You should have test A, B, C, D, and the expected result out of each one of these tests. That functional test says that, okay, this payload is ready to go. Once you verify that your functional test works, then you do a calibration, an initial calibration, so that you get your results. Then you start going through a specific sequence of system testing. Thermal first, pressure, and then shock. Your payload has got to successfully complete and operate properly within specs for all three tests in a row. If it fails any one, if you go through thermal, fine. You go through pressure, fine. If you go through shock and there's a problem, you have to fix it and you start all the way from the beginning. You start with your functional test, your calibration, you go through your thermal test again, your pressure test, your shock test. You have to go through all three tests before you're done with this thing. So make certain that you give yourself plenty of time to complete your thermal testing and your pressure and your shock testing as you go through these things, and make certain that you have a payload fully flight ready before you even start this stuff. All right. All of these tests are documented in your FRR. Finally, you have a mission operations and data plan. This is basically what is it that you're going to do to get your payload flight ready, and then what you're going to do with the data analysis. How are you going to analyze your data? Where are you going to get your data from? What's your software that you're going to be using for the analysis, etc. So you need to document and write that up in your CDR as well. Communication is important, right? Ancient saying, if it is not written down, it did not happen. Oh, I soldered this together last week. Oh, where did you say that? Where did you write that down? Where is that in your report? It didn't happen, right? You need to be able to write it down. The corollary to that, if you wrote it down, you agreed to do it, right? I wrote down that I will be doing the software development of subroutine A. 3 weeks later, where is it? You agreed to do it, right? There's a real reason why we do these documents and why we do this communication. You have effort across a number of stakeholders, not only yourselves, but also your faculty advisor and also LACES management. You've got to communicate how you're going to agree to proceed. You've got to be able to track progress. That's why we require the PDR, CDR, and FRR documents from you. And you got to make certain that all your groups are working together coherently in your team. Okay. That written documentation is glue. It stabilizes your project, right? It helps you develop end-to-end thinking, rather than going from crisis to crisis to crisis. By writing things down and documenting it, you provide a methodology for looking at the entire project at once. You have to understand what your roles are, what your tasks are, what your schedule is. That has to be done in sequence. And also equally important is proof of performance, right? And finally, reports and presentations set your precedent for acknowledgement of your effort. Have you ever heard of the phrase publish or perish? That's exactly what's going on, right? When you write something down and you document it in a report and a presentation, you get credit for having done that work. If you don't write it down, if you don't present it, if you don't write a report, then who knows what you did? So that kind of communication is important. That's why we're so, why we incorporate this into this project immediately. There are 3 major reviews, the PDR, CDR, and FRR. We include these pre-PDRs and pre-CDRs to break it up a little bit. And you can see sort of the schedule that's in here. We talked about this before, right? Each team must prepare the written document. We only care, LACES management only cares about the written document. Your internal work at your institution, that institution may require oral presentations. So you need to work that out at your institution. Each document review requires different emphasis. So the PDR, as I mentioned before, is going to be focused mainly on things like objectives, requirements, goals, and high-level system design. The pre-PDR is in fact focused exclusively on objectives and requirements. And so you need to really complete that PDR before you move on to the system design elsewhere in the PDR. So you need to be on top of this stuff. So here's sort of the topics that end up being in the PDR. I pointed out the ones where the pre-PDR emphasizes it, so you can see what's actually included in here. These templates will help you guide what you need to do. CDR goes through and is, like I say, your build to order menu, provides all the final details as to where you be, where you're going with your payload, your final circuit designs, your data formats, your software flowcharts, critical, maybe even including listings of critical subroutines that are particularly important. Things like that, all your flight software and ground software, how you're going to be analyzing things, how you're going to do your calibrations. That should all end up being in your CDR. The pre-CDR includes resolving issues identified in the PDR. It also includes the results of your prototyping and proving your design is there, as well as completing your system design and interfaces. And then the CDR would include your final task and scheduling and assessments, risk management, and a preliminary MODA plan. And then finally, the FRR is needs to provide the evidence that your payload meets your advertised requirements, that it is safe, that it isn't going to fall apart, and that it will also perform properly. That's really the goal of that FRR. It should have the as-built configuration. It should have the results from your environmental testing. It should show how your calibrations were performed and what their results were. We will use that FR to determine if there's any impact on any other payloads, to identify whether or not you would be, whether or not there's anything that still has to be resolved before allowing you to fly on that. So these are the topics, right? One thing to keep in mind is that the only time that this is the oral FR presentation is what we will be requiring when we go to flight, right? You may have other oral presentations on other reviews from your own system. In order to fly, you are going to have successful PDR, CDR, and FRR documents and a successful FRR oral presentation, right? You got to keep that in mind. So you got to be serious about this as we go forward. As I mentioned before, you'll have 48 hours to produce a post-flight science report. You're going to have to include a summary of your payload, what it is, because this will be the first time that these CSBF guys will be understanding anything about your payload. So you're going to have to tell them what you're doing, why you're doing it, as well as how your payload performed and what your flight results are. Right? I would recommend that you get the forms, that the basic structure of your science report be completed before you even leave for a CSBF, so that all you really have to do is sort of drop in your results. You also better have all of your ground software analysis ready to go so that you have that. We will provide you, well, and you should have as well, your own GPS information, but we'll also provide a time to altitude converter for that flight, that particular flight that you're on. So you'll have that. Typically, this is the schedule that we have for the flight. We will travel to NASA CSBF, Palestine, Texas. Look it up on Sunday. Monday will be the FR presentations and then preparing for launch. Tuesday would be flight ops, including launch, flight, and recovery. Wednesday, you'll have data analysis. Thursday, you'll have your science presentation. If all goes well, we can leave for home Thursday afternoon. If there's a delay in the launch or something else, then Friday is always a contingency. So always plan. While it's very likely that we'll be back by Thursday evening, do not plan on that. Plan on coming back Friday evening, and then if we get back earlier, that's great. Okay. All right. So that's all that I have.